Ismail Gadzhiev and I represent Convolutional Institute of Nuclear Physics and I'm a PhD student of Lomonosov Moscow State University. My report is called a Convolutional Hierarchical Neural Network Classifier. Hierarchical Convolutional Hierarchical Neural Network Classifier is a modification of Hierarchical Neural Network Classifier, and it solves multi-class classification problems. And it is a tree in each node of which there is a neural network that is trained on a certain subset of all classes, and class groups are formed adaptively. On the right side you can see the image of the tree obtained during training of hierarchical neural network classifier. In each node there are grouped classes. Let me tell you about HNNC training algorithm. The neural network in each node is a weak multilayer perceptron with a small number of neurons in a single hidden layer solving a classification problem with one hard encoding at the output. After a predefined number of training epochs, the statistics of the network output on the training set is analyzed. If some classes are consistently mixed up for the majority of voting input partners of a class, such classes are merged by modification of the desired output. The cycle training class merging is repeated while classes continues to merge, and the numbers of classes is greater than 2, and until the network error for the modifier class set on the validation dataset stops to decrease for a predefined timeout. For each class group that has been formed by class merging, a new node is trained. So, convolutional hierarchical neural network, or classifier, is designed to solve multi-class image classification problems. Each node contains a convolutional neural network instead of multilayer perceptron as in regular hierarchical neural network classifier. The hierarchy of the classes obtained with weak CNNs can be used with strong CNNs to improve the recognition rate. For the purposes of testing, we use two tasks, Cypher 10 and Cypher 100. Those are well-known benchmark datasets, consisting of images of 10 and 100 classes respectively. On the right side you can see the examples from these datasets representing different animals, vehicles, and etc. The training of convolutional hierarchical neural network classifier consists of two stages, and on each stage we use different types of CNN models. Those are the weak CNN and the strong CNN. The weak CNN used at first stage of the algorithm is shown on the first image. The single convolutional layer contains 3 neurons, and each dense layer contains 3 neurons. The strong CNN is used on the second stage of algorithm, and each convolutional layer contains 32 neurons, and each dense layer contains 10 neurons. Let me tell you about the first stage of training. The weak CNN is trained on the initial set of the data. After a predefined number of training epochs, the classes which get mixed up are merged. This cycle training class merging is repeated while classes continue to merge, and the number of classes is greater than 2, and until the network error for the modified class set and the validation dataset stops to decrease for a predefined timeout. For each class group that has been formed by class merging, the described algorithm is applied recursively. And this image displays an example of class hierarchy for Cypher 10. As you can see, it is similar to the intuitive hierarchy that can be constructed by human. And the next image shows class merging diagrams for Cypher 10 in each node of a convolutional hierarchical neural network classifier. The second stage is training strong models. A CNN with stronger parameter values is placed in each node of the resulting hierarchy, and the training is repeated without class merging. The weak models are effective for tree construction, but they usually result in low recognition rate. Use of strong models allows one to reduce the effects of error multiplication when moving down the tree. And one more detail, pattern voting for construction of a hierarchy. To determine which classes of the network mixes up most often, voting of patterns of each class is performed on the training set. If most of the patterns for class I are assigned to class J, then these two classes are merged into one. There is a problem here: influence of random weight initialization on the voting. This results in random merging of the classes. To cope with this problem, we use thresholds. The thresholds are introduced to solve the problem of random merging. The first threshold is activation threshold. The votes only of those patterns for which the maximum activation of the output neuron is greater than activation threshold are taken into account. And the second threshold is voting patterns share threshold, and class I is merged with class J only if the percentage of class I patterns that voted for class J is greater than voting patterns share threshold. And there is a question of selection of the activation threshold, and we introduce two methods of selection of the activation threshold. First is setting fixed threshold for all nodes. The optimal value of the threshold is determined by enumeration. The second is setting the threshold equal to the upper boundary of the output activation localization area with random initialization. So there is a formula here for this localization area that involves such parameters as mean and standard deviation and some coefficient selected by enumeration. At this slide, we present the setup for testing for various activation values, for various threshold values. So the benchmark dataset is Cypher 10. There are parameters of weak CNN and strong CNN. For optimization, we use Atom with learning rate 0.001. And for each pair of threshold values, we perform 5 runs, and the results are average across all runs. And for the first and second algorithm stages, the training set was split into two parts in 1:4 proportion. So this slide demonstrates that threshold values control the height of the tree. As we can see, as we increase thresholds, the height of the tree is decreased. This slide represents the dependence of the accuracy on activation thresholds for different thresholds for voting share. And we can see that the results are unsatisfactory. This slide represents the dependence of accuracy on activation threshold for different thresholds for voting share for the second stage, and the second stage of the algorithm provides a cardinal improvement of the results. And the next slide is the dependency of accuracy on the coefficient in the formula for adaptive activation threshold for different thresholds for voting share. And the results here are also unsatisfactory because it's only the first stage. And here's the second stage. And as you can see, there's no pronounced dependence of the results on the threshold values. So the conclusion: we have introduced a novel version of the hierarchical neural network classifier, a convolutional hierarchical neural network classifier, and an algorithm for its construction. And the necessity of the second stage of the algorithm has been demonstrated. The obtained class hierarchy can be reused in other algorithms. Introduction of two types of threshold demonstrated no pronounced dependence on the threshold values. However, the best result for Cypher 10 problem were obtained for the two-stage algorithm with adaptive activation threshold with k is equal to 1 and voting pattern share threshold equal to 0.3. The algorithm requires further investigation of the optimal methods for setting of the threshold values at the first stage and of optimal parameters at the second stage. Testing on other benchmark problems is also required. Thank you for your attention.